Good afternoon all. Welcome to the lecture of Discrete mathematical structure. Okay, so in last lecture we have seen what is the lattice and some examples of lattice. That from Hasse diagram we have checked whether it will be a lattice or not. Okay, now lattice is nothing but it is a poset in which every two element subset has a least upper bound and greatest lower bound. That is, every two element subset has a supremum and infimum. Then corresponding poset is called as a lattice. Okay. Now today we have to see some properties of lattice. Okay. Let's start. So first properties of lattices. Actually, we have to see that if they are of the theorem type. Okay. Since they are actually properties, but we have to see its proof also. Okay. Properties of lattices. Okay. Now in that we have to first see one theorem. If L be a lattice, then for every small b in first A join B equal to B if and only if and only if A precedes B. Second one, A meet B equal to A if and only if A precedes B, and finally last one will be A meet B equal to A if and only if and only if A join B equal to B. Okay, so here we have just given that capital L be a lattice and A and B are any two elements of the lattice L, and from this we have to prove these three results, that is A join B equal to B if and only if A precedes B. Okay, now and if we prove first one, A join B equal to B if and only if A precedes B, then A will be obviously A. Okay, and from first one the B2 will be obviously true. Okay, now if first two are true, that is A join B equal to B whenever A precedes B, and A mid B equal to A whenever A precedes B, and its converse also. If A precedes B, then A mid B equal to A and A join B equal to B. Therefore, from combining the first two properties, the third one will be obviously true. That is A mid B equal to A. It means A precedes B, and A precedes B implies A join B equal to B. And similarly, A join B equal to B implies A precedes B, and A precedes B implies that A mid B equal to A. So if we prove the first one, then from first one we can make second one true, and if first and second one both are true, then combining these two, C will be obviously true. So see its solution. Proof. First, let us take, here we have to prove that A join B equal to B if and only if A precedes B. So here first we will take A join B equal to B. Then A precedes B equal to A. So here first we will take A join B equal to B. Then A precedes B equal to A. Then A mid B equal to A. And finally last one will be A precedes B equal to A if and only if A precedes B. And similarly A join B equal to B whenever A precedes B and A mid B equal to A. And in the definition of lattice we have seen A precedes A join B always. Okay, and here we have A join B equal to B. Just put the value of A join B as B, which implies A precedes B. Okay, so if we take A join B equal to B, then A precedes B obviously. Now its converse part. Conversely, A precedes B. Okay, as A precedes B, and we know that every element precedes itself since it is a lattice. Lattice means it is a poset. Poset means it is a it holds the three properties, that is reflexive, symmetric, so antisymmetric and transitive. As it is symmetric, sorry, reflexive, then every element precedes itself. See, then since B precedes B, since it holds the reflexive property, then each element is related to itself under the given relation precedes. Okay. Now, which implies B is an upper bond of, by the definition of upper and lower bond, B is an upper bond of two elements A and B. Since A precedes B and B also precedes B. Okay, and precedes will be our given relation. Then by definition of upper bond, B is an upper bond of A and B. Whether it is list or not, that that we don't know. But it is a just an upper bond of two elements A and B. Now, so by definition of list upper bond, we have A join B precedes B. Since A precedes B and B precedes B, then by definition of list upper bond, B is an upper bond of A and B, where A join B is the list upper bond of A and B, which implies A join B precedes B. Since A join B is the list upper bond of two elements A and B, which is from the definition of upper bond. Okay, so A join B precedes B. Again, since A join B is also upper bond of two elements A and B. A join B is an upper bond of small a and B, which implies B precedes A join B. Which implies B precedes A join B. Now combining these two, A join B precedes B, B precedes A join B, and as it is posted, it holds the antisymmetric property. That is, A precedes B and B precedes A, then A must be equal to B. As here, A join B precedes B and B precedes A join B, which implies A join B is nothing but B, and that is we have to prove, and hence the proof. Hence proof. Okay, so first property will be hold here, since first part we have taken A join B equal to B and we have proved that A precedes B, and in second one we have taken A precedes B and we have proved A join B equal to B. So from this one we say that A join B equal to B if and only if A precedes B, since both the part are true. Now we have to prove second one, that is A mid B equal to A if and only if A precedes B. By using the definition of greatest lower bond, this will be obviously true from the first one. So B will be similar to A. Similar to proof of A. Now see. So first and second will be proved. Okay. So A join B equal to B if and only if A precedes B, and A mid B equal to A if and only if A precedes B. So in third one, just take first part A mid B equal to A. If we take A mid B equal to A, then obviously we get A precedes B, which is from second one. And if A precedes B, then from first one A join B equal to B. So if we take A mid B equal to A, then A join B equal to B. In second part, let's just take A join B equal to B. If we take A join B equal to B, then from first one it is A precedes B, and if A precedes B, that from second one A mid B equal to A. So both the part are true. Combining A and exams are equivalent. Hence, all the three above above three exams are equivalent. Okay. So if we take any one, then obviously the remaining two will be true. If we take A mid B equal to A, if and only if A join B equal to B, then obviously the remaining two will be true. Okay. Same for remaining cases. Now here are some properties. If capital L be any lattice, capital L be any lattice, then for any ABC belonging to L, then for any A comma B comma C belonging to lattice L, first one, idempotent law. Idempotent law. That is idempotent. We have actually seen idempotent law in mathematical logic. It is same as in mathematical logic. A join A will be equal to A, and A mid B will be equal to A mid B will be A mid A will be equal to A. Now second one will be a commutative law. Commutative law. In that one, A will be A join B equal to B join A, and B is nothing but A mid B is equal to B mid A. So either we can find out A mid B or B mid A. Both are the same things if it is closed under commutative property. Third one, associative law. First one, A join B join C is equal to A join B join C, and B1 A mid B mid C is equal to A mid B mid C. And last fourth one will be a absorption law. Okay, and that one says that A join A mid B is equal to A, and A mid A join B equal to A. So this will be a absorption law. These are the some important properties of lattices. Okay. So actually these properties we have seen in mathematical logic also, but there the meaning of these notations, this one and this one, is different. There this one is nothing but or, and this one is nothing but and here this one is join and this one is meet. Now next theorem, let L precedes be a lattice, be a lattice, then for ABCD belonging to L, then for ABCD belonging to capital L, first one, A precedes B implies A join C precedes B join C. Second one, A precedes B B meets C. E precedes B and C precedes D implies A join C precedes B join D, and last one, A precedes B and C precedes D implies A meet C precedes B meet. Okay. So here L precedes B a lattice. Then for any four elements A, B, C, D belonging to capital L, we have to prove these four properties. Seeds proof will prove the first one. The first one will be proved. The second one will be obviously true. Okay. Now first one. From previous theorem we know that from previous theorem we have A precedes B. We have proved that A precedes an element B if and only if A join B is equal to B. We have proved this one. In the last theorem, the first property is nothing but A precedes B if and only consider A join C join B join C is equal to A join C join B join C, which is nothing but A join C join. This B join C can be written as C join B, which is from the commutative property. Since if L be a lattice, then the lattice L holds the commutative property, which is from commutative law. Commutative law. Okay. Now this can be written as A join C join C join B, which is from associative law. Associative law. But from absorption law, sorry, idempotent law, C join C is nothing but C. Since absorption law says that if L be a lattice, then A mid B will be equal to A and A join A will be equal to A. So as L be a lattice, then C join C is C. So A join C join B. Now, which can be written, which is from idempotent. Okay. Now, again we have to use the commutative property on C join B. A join B join C, which is from commutative. But as L be a lattice, then A join B join C can be written as A join B join C, which is from associative law. Associative law. We have to just write it in a proper way. Okay, now, but we have given that A precedes B, and if A precedes B, then A join B will be equal to B, which is from the above. Here we have taken. Then from star, if A precedes B, then A join B will be equal to B. Then just put the value of A join B as B join C, which is from star. So actually we get A join C join B join C equal to B join C. Now from this result, if A join B will be equal to B, then A precedes B. Here let us take this element will be equal to B, then A precedes B. So here A is this value, B is this value, then and A join B will be equal to B join C. That is here we get A join B equal to this B. Then A must precedes B. Therefore from this one we get A join C precedes B join C, which is from star, and that is we have to prove and hence prove. Okay, so first property will be proved here, so which is from the join operation. Now similarly we can write for a meet operation also. Just we have to consider here instead of join meet, then we will get the same result. Group of 2 is similar. Group of 2 is similar to this one. Okay, now third one. Again we know that A precedes B implies and implied by A join B equal to B, and we have given that C precedes D. Then by here we get A join B equal to B and C join D equal to D. Join B join B, join B join B. So which is nothing but A join C join B join D, which is from associative property. Associative law. Just we have to use the properties. Now it can be written as A join B join C join D. C join B will be equal to B join C, which is commutative law. Commutative law. Now next, it can be written as A join B join C join D, which is again from the associative law. Associative law. But we know that here we have in third one we have given that A precedes B and C precedes D, and as A precedes B, we know that A join B will be equal to B and C precedes D, which implies C join D equal to D. Just put that values. A join B will be equal to B and C join D will be equal to D, which is from star 1. Take this one as a star 1. This combining these two is star 1. So A join B equal to B and C join D will be equal to D. Just we are putting this value. So actually here we get A join B, sorry, A join C join B join D is equal to B join D. Again we have to just use the property. Here this will be considered A, this will be B. Okay, and we know that if A join B will be equal to B, then A precedes B. So here A join B will be equal to B, which implies A precedes B, but A is nothing but A join C, which precedes B join D, and which is from star or star 1. Okay, and hence the required proof. Result. Hence, now proof of 4 is similar. Okay, now the next theorem will be in any lattice the distributive inequalities, the distributive inequalities first one, A meet B join C is equal to, sorry, is greater equal to A meet B join A meet C, and in second one, A join B meet C is less equal by, that is, and we have to prove the distributive inequalities. These two, A meet B join C is greater equal by A meet B join A meet C, and A join B meet C is less equal by A join B meet A join C. See its solution. First one, we know that A meet B is less equal by, or it always precedes A. Okay, and also A meet B precedes B, since A meet B is less than or equal to A, and which is also less than or equal to B, and B is precedes always B join C, which implies A meet B precedes B join C. So A meet B precedes A and A meet B precedes B join C, which implies A meet B is a lower bond of is a lower bond of two elements A and B join C. A B join A and B join C. Okay. Now, which implies A meet B precedes least upper one and greatest to lower bond. Okay. So here we have to use the definition of least lower bond, as A meet B is a lower bond of these two elements A and B join C. Therefore, A meet B must precedes A meet B join C. Take this one as the equation 1. Again, A meet C precedes A and A meet C precedes C also, and C precedes B join C. B join C. That is A meet C precedes B join C. Okay. Again, just by definition of lower bond, A meet C precedes A meet B join C. Take this one as equation 2. Now from equation 1 and 2, A meet B precedes A meet B join C and A meet C precedes A meet B join C, which implies that 1 and 2 shows that A meet B join C is an upper bound and A meet C. Okay, which is from equation 1 and 2, which implies A meet B meet A meet C precedes A meet B join C, which is from the definition of upper bound. Okay, so here we get A meet B meet A meet C, sorry, A meet B join. Here we have to take the join, since we have to prove that A meet B join A meet C precedes A meet B join C. So here, as A meet B and A join C both are less equal by this A meet B join C, then if we take its join, then it is also less equal by A meet B join C, which is from the definition of upper bound. Okay, so first property will be true, hence the proof that is we have to prove. Now, proof of second one is similar to this one. The proof is similar to one. Proof is similar to one. So both the properties will be true. The next concept is a sublattice. Sublattice. Okay. In this subset, of a lattice L is called a sublattice of L if A and B are any two elements of L dash, then A join B and A meet B, both are the elements of L dash. Since A join B is nothing but the least upper bond and A meet B is nothing but the greatest lower bond. So any non-empty subset of L dash of a lattice L is said to be a sublattice of L if it is itself a lattice. That is, it is closed under greatest lower bond and least upper bond. Okay, that is the algebra L dash with operations join and meet is a sublattice is a sublattice of L meet join if and only if L dash is closed under both the operations meet and join. Closed under both operations meet and join. Okay, so any non-empty subset L dash of a lattice L is said to be a sublattice of L if it is closed under both the operations meet and join. Closed under both the operations meet and join means if we take any two elements A and B from L dash, then A meet B is belonging to L dash and A join B is belonging to L dash. From definition, it follows that a sublattice is itself a lattice. Self is a lattice. ओके, जर कोणताही एखादा सबसेट घेतला एलचा, जर तो स्वतः लॅटिस असेल तर तो त्याचा सबलॅटिस असेल. एक्झाम्पल, let S be a set and L equal to power set of S, intersection and union. So here we have given the two operations meet and join as meet is nothing but intersection and join is nothing but union. Now if S is equal to A, B, C, D, then and set which contains the element phi A, AC, C and A sublattice. Okay, so here we have taken one element, one set S which contains the four elements A, B, C, D, and we have taken one set which contains these elements, five elements, phi A, doubleton AC, singleton C, and ABC. Now if we take any two elements among these five elements, its intersection and union is always belonging to that set. Okay, so it is closed under both the operations intersection and union, therefore it is a sublattice, which is from the definition of sublattice. For example, if you take AC and ABC, then its union will be ABC, which is again in same set, and if you take its intersection, then its intersection will be AC, and which is belonging to the same set AC. Similarly for these two sets, in A intersection AC, A which is belonging to this one, A union AC is nothing but AC, and which is again in same, which is true for all the two elements belonging, two elements which are present, which are belonging to that set. So intersection of any two element and union of any two element in that set is belonging to that set itself, therefore it holds the definition of sublattice and hence it is a sublattice. Now we will take one example of a subset of S which is not a sublattice. But phi singleton A, singleton B, singleton C, and doubleton BC would not be would not be form a would not form a sublattice sublattice as singleton A union singleton C is nothing but doubleton A and C. Since union of these two sets, singleton A and singleton C, is nothing but singleton doubleton AC, but doubleton AC is not belonging to this set. Okay, so it does not hold the definition of sublattice. It contradicts to our definition and is not there. That's it. Is not there, and hence it is not a sublattice. Now this will be the definition of sublattice. Now the next concept will be nothing but complete lattice. A lattice is called a lattice is called complete if it has a least upper bound and greatest lower bound. Okay, so any lattice L is called a complete lattice if each of its non-empty subset has a least upper bound and greatest lower bound. That is, it has a supremum and infimum. ओके, कोणताही एक लॅटिस हा कम्प्लीट लॅटिस कधी होईल जर त्याचा कोणताही एक सबसेट घेतला. त्या सबसेटमध्ये किती एलिमेंट आहेत माहित नाही, पण कोणताही सबसेट जर घेतला त्याला जर लिस्ट अप्पर बॉन्ड आणि ग्रेटेस्ट लोअर बॉन्ड येत असेल तर मी त्या लॅटिसला काय म्हणणार, कम्प्लीट लॅटिस. नाव नेक्स्ट विल बी अ डिस्ट्रीब्युटिव्ह लॅटिस. Distributive lattice. A lattice L with operations join and meet is called distributive lattice. If for any ABC belonging to L, if for any A, B, C belonging to capital L, A meet B join C is equal to A meet B join A meets. If it holds the distributive property, then it is called a distributive lattice. And A join B meets C is called, sorry, A join B meet A join C. So any lattice L is called sub distributive lattice if it holds any one among these two properties. Okay. Now the last concept, which is nothing but the modular lattice. A lattice L join meet is called distributive sorry it's called modular lattice. This is, we have seen already the, it's called modular if join B mid C is equal to A join B mid C for A precedes B whenever A precedes C for each and all ABC belonging to capital. Yeah. Okay. So any lattice L with operations meet and join is called a modular lattice if A join B mid C is nothing but A join B mid C whenever A precedes C for any elements ABC belonging to L. Then we say that the corresponding lattice will be a modular lattice, and this will be the last concept in our lattice. So here we have all the 4 units now. Best luck for the exam and thank you for watching the lecture.